Okay, thank you. So it's a great pleasure to be back in Vienna. This is my second time here. And the topic I'm going to present you is, it came after the work. It's a continuation, let's say, of what I presented at the online One World optimization seminar. So there will be a couple of slides which intersect my presentation, but I hope to present something new. And it's about error bounds for mean-payoff Markov decision processes. So the talk will consist on two parts. The first one is just a short introduction to mean-payoff Markov decision process, just to set up the notation in case you're not familiar with that. And then I will focus on the techniques that allow to derive error bounds. And by this, I mean finite-time error bounds. So I will study an algorithm which was proposed years back by Abunadi, Betsekas, and Borkar. And I will propose a methodology to come up with precise bounds on the error that you achieve after n stages of running your algorithm. So it's finite times error bounds. So let's start. So as I said, two parts, mean-payoff Markov decision process, very short. So we're considering a Markov chain, which is under our control. Everything will be finite, so I have a finite state space, which I call S, or script S, and I also have a finite action space. At every stage, I'm in a given state, which I observe, and I have to take an action. And the goal, so when I take, let me see if I can put here, once I take an action A, if I'm standing at state I, the process will jump to a new state J with a certain probability. It's a Markov chain which is controlled by our actions. And as you do that, then you recover some rewards, which is denoted by R of J. So at state I take action A, I jump to J, and I get a reward of RJI. And what is our goal? Well, first, what is the evolution of the chain? If I give you a starting state I0 and I prescribe a sequence of actions, I'm thinking of an infinite run of the Markov chain. If I prescribe a sequence of actions, then the state will evolve like this as a control Markov chain. And what is our goal is to find a stationary policy. That means a map that takes that takes states to action. It prescribes what should you do at every possible state that you encounter along the evolution. So you're looking for a stationary policy. We can discuss why stationary, but for the moment, let's just take it for granted. And I'm looking for such a policy that when I apply this control, when I choose my actions according to mu, then what I get is the maximum reward evaluated in terms of long run or long-term average payoff. So what do? I look at the streams of rewards. I average over 0t. I take that average. Of course, that's random. I take the expectation of this, and I take the long run. I look for t very large. That's the objective function. Minimize the long-term, limit a priori, the long-term expected mean payoff. Clear so far? Okay, there is a huge number of applications of these ideas. There are different objective functions also. Instead of taking the long-term average, you can also take discounted payoffs. But for this talk, I will concentrate on this objective function. And in Puterman, you will find at least 2 chapters of applications. So what about Bellman's equation? We are in a dynamic programming setting, so we can hope to find a certain recursion that allows us to simplify the calculations of optimal values. So it is a standard assumption, not very strong, but still is an assumption, that it's called unit chain. It prescribes that every fixed policy, once you fix the policy mu, the random, the Markov change that results, the induced Markov change, has a single recurrent class. That will ensure that there is a unique invariant measure and that the C0 averages converge to the invariant measure. So in that case, the expected long-term average of payoffs, first, is not a limit, it's just attained as a limit. And moreover, it only depends on the stationary distribution at the end. So everything that occurs in the transient stage is irrelevant. In particular, it doesn't matter where you start from. You start from a different state, the value, this R mu I0, doesn't depend on the initial state. And that's a problem because contrary, well, I was expecting to write there, but maybe it's better to, better to speak. In the discounted case, you can write very easily, much easier than the mean payoff. You can write Bellman's equation, which distinguishes states. The value is not the same for every state. And from there, you can derive the optimal policy. Well, it is not the case here. In this case, the long-term average forgets about the state, so it doesn't give you any information on what should you do at a given state I0. So this requires a lot of additional analysis that you can also find in Puterman. All of this is quite classical. That you have to, instead of looking at the optimal value, you have to look at oscillations around the optimal values. And doing that sensitivity, you come up with a different type of Bellman's equation, which is written here. So let's introduce this map HQ. So Q will represent a matrix which has an entry for every state and action. We'll give you an interpretation immediately. So how do you compute, given such a matrix that gives you, let's say, the reward at state I and action A? From a given matrix A, I will compute a new value, HQ of IA, by taking the expected value of the one-step reward plus the future. And the future is evaluated by the maximum. So you assume that in the next stage, so interpret I as the current state, interpret CIA as the next state, which will be drawn at random. So once you have this random realization, you adapt by choosing the best action according to your function Q. And then there is this minus R bar. Let me remind you what R bar is. I didn't. So R bar will represent the optimal value of your problem. You can prove that it exists. There exist optimal policies. It's very simple because everything is finite here. So you have only a finite number of policies. So it's a huge number, but you just evaluate every possible policy and you take the best one. Okay? So existence is not an issue. So I will denote R bar this value. And so I introduce this map, which has some feeling of type of recursion. You take the current payoff plus the future, except that the future is not discounted here. And this is representing the fact that you're only interested in the long-term averages. So there is no discounting, or if you want, the discount factor is 1 here. But then you have to take off this R bar, and that's a problem because R bar typically is unknown. So you introduce this map, and so all of this is known. The optimal value, R bar, well, it was there. This is the only real for which this Bellman equation, so the fixed points of H, exists. So if, yes, no. In the states R, S cross A. Matrices, but they're not stochastic. They just represent values, optimal values, let's say. Yes. Take any rectangular matrix, let's say what you believe to be your optimal cost, and then you update by this. This is cost. Okay? So in linear space, in R, S cross A. No constraints. So if you look at this map, well, it turns out that this map has a fixed point only if and only if you plug R bar the optimal value. So if you plug in any other value, there is no solution. And for R bar, there is a solution, and moreover, it is unique up to constants. Of course, if you take a Q and you add a constant, well, the constant adds on both sides, so you cannot expect to have uniqueness of fixed point, but you have existence. And to ensure existence, you have to be careful to put here the right R bar. If you miss the R bar, then there is no solution. That's another problem to be aware of. Next observation is that this function is monotone with respect to Q. So if I increase Q, everything increases. And it's transparent to constants. So it's automatically non-expansive for the infinity norm. That's another problem. Many fixed points algorithms, they work in Hilbert space or with thick convexity or even strong convexity of the norm. Well, here we lose that. We have to deal with this infinity norm, which is an additional difficulty. And as I said, there will be a unique fixed point up to a constant. Once you have the Q to derive an optimal policy, it's very easy. You take the Q that you computed, the fixed points, and for each action I will choose what is the action A that maximizes this function Q. So the goal is, how do we compute Q? Or how do we solve this equation? So here's a simple example to give you some flavor. So suppose that I have only two states, 1 and 2. Let's say that 1 is a bad state, 2 is a good state. And I have two actions. I will assume that the rewards only depend on the final state. So if you're at state 1, you get a reward of 1. That's the final state. So if you jump to 1, you immediately receive €1. If you jump to 2, you immediately receive 10 euros. So of course, I would prefer to be in state 2. So these rewards, they do not depend on my action, they do not depend on the current state, but they depend on the state which I will reach. So of course, I want to maximize the probability of being in state 2. And the actions will only control the probabilities. If you take action A1, so in these arrows, you have the probabilities. From 1, you jump to 2 with probability 0.7. You stay at 1 with probability 0.3, and so on. So I think we can all guess what's the optimal strategy here. What would you do if you were in state 1? Remember that we want to jump to state 2 because it's a higher reward. So I want to just maximize the probability. If I take action A1, this will occur with probability 0.7. Here, only probability 0.1. So certainly at state 1, I should choose action 1. And at state 2, I want to stay at 2, so I will choose action 2. If you do that, you compute. Your R bar is 71/8, and that's it. Simple, you can solve everything, and that's it. The problem is that in many situations, you don't have access to the probabilities. You know that there is some random process behind, but you don't know the probabilities. You only have access to simulations, to samples. And the question is whether we can learn an optimal policy. So here's the map again. It has two difficulties. The first difficulty is what I just said. The probability may only be accessible through sampling. Well, the idea is very simple in that case. You take this expectation, instead of considering the average map, you just sample. So you replace the expectation by some simulation of this random variable, the next state. The second problem is that the optimal value that appears here is unknown. And it's of no help to try to put something which is similar to R bar. If I miss the good R bar, I will not converge because there is no fixed point. So what Abunadi Borka suggested for that case is to replace R bar by a function of Q with some properties of homogeneity, of just takes out the constants. So if I take f of Q plus a constant, the constant comes out. And then replace, so do a fixed point iteration for this HQ by this mean. So if I start from a previous iterate Qn minus 1, I will average my previous estimate with the new estimate with some coefficient alpha n to be specified. And here replace not h, but h sampled, and moreover with R bar replaced by f of qn minus 1. That was the proposal of Abunadi Bertsekas-Borkas in 2002, and in general Q-learning was proposed by Watkins and Dayan in the 1990s. Well, here non-uniqueness is about displacement by constants. So I want to preserve that. Sorry? R bar is also positively homogeneous, yes. Maybe you could do it. In fact, you don't even need this. You only need that f is increasing. It's an increasing function of for any given q, if I take a constant c, I need that this increases with c. So that's the algorithm. That is called RVI Q-learning. RVI stands for relative value iteration. So it's a value iteration, but not in absolute value, but in relative values because of this, this fact that you have to do higher order Bell-Mass equation. So just an observation, the modified, so if I look at this modified map, which is just the expected value of this, when I take expectation with respect to the noise, this function, this map, well, now has a unique fixed point. Before we had uniqueness up to a constant. Now you have a unique fixed point. In fact, it's the only element of the original map, it's the only fixed point of the original map H, which satisfies in addition f of q star equal R bar. So somehow you expect that along the iterations, this f of qn will converge eventually to the good optimal value. So you don't take a fixed R bar, but you adjust it along the iteration. That's the idea. So maybe one example here, the same as before. If you take the function f of q, just the maximum of qia, the only fixed point q star is this one. And you see here the 71 over 1 over 8 is the exactly f of q star, which is the optimal value. And if you do some simulations, so I don't know. Probably not, but I'm not sure. Did I say that? Yes. We have lost non-expansivity because of the introduction of f. But as you will see, it's not a big issue. We can get around this difficulty by a certain coupling. So here are the simulations. So I'm running the RVI Q-learning trajectories. Here I'm taking alpha n, decreasing step sizes. And here I'm plotting the f of qn. These are different rounds. You see that they converge to R bar, which is here, 71 over 8. Well, seems to work in practice at least. What about convergence of iterates? Well, if I take qn minus h of qn, of course, this on every round, this is a different random realization. So I take the expectation. In fact, I don't take the expectation. I just average over 100 runs. And I see that there is a scaling here. The expected error, this is the fixed point residual, it seems to go to 0 at least as fast as square root of log n. This is empirical. Maybe faster, you know, even scaled by log n, there is still a tendency to decrease. The exact rate, I don't know. So here's another example. If you take a polynomial step size, again, decreasing, there is more noisy iterations, but the value still seems to converge. And the rate now is like square root of 10 of n. I must say that these are very slow rates by any standard. Usually one believes that polynomial or power forms are better than log. In this case, I would be careful to state a claim. If you plot square root of 10 against log n, it takes n pretty large for the square root of 10 to beat the log. Asymptotically, yes, but you need something like 10 to the 30 iterations. So it's, the log might still be competitive, but they're both slow. So all of what I showed here can be proved formally, including the rates, and more than the rates, error bounds. And how do we do that? We observe that we can cast the RVI iteration as a special case of these Krasnoselski Mann iterations, except that there is a stochastic noise. So how does it go? Now I'm going to a general setting where I have a map T from RD to RD, which is non-expansive in some norm. My norm of interest will be the norm infinity, and the operator will be H. And the assumption is that the values of this operator can only be computed up to some random additive noise. And I will do this type of iterations. The next iterate is the average of the previous one, and this noisy observation of the map. Standing assumption, the alpha n's are assumed to be a sequence where the sum diverges. Sometimes alpha a, most of the time alpha k will go to 0, but for the moment, no. And the noise, I'm assuming that it's a martingale difference, so basically that it has 0 mean in some filtration, and bounded variance, finite variance, sorry, not bounded. And this is essential. We must allow variances to grow to infinity, because this is what happens in the Q-learning. So I have Q-learning is exactly of this form, except that the noise may have a variance that grows with the iterations. So how much time do I have? 5 minutes. 5 minutes. Okay, I will speed up here. But this is the part that I already spoke, but just for the sake of those who haven't seen this before, let me just give you a rough idea of how do we deal with these iterations, how do we estimate error bounds. So the norm of the residual, this is what I want to bound. And suppose first that there is no noise, so deterministic case. Then it's easy to observe that your xn is an average of all the previous iterates. So you can write it explicitly as an average, and then if you can estimate the distance from any two iterates, xm and xn, let's say, then it's pretty easy to compute an estimate of xn minus t of xn, because xn is an average of the previous images minus t of xn. You just triangle inequality, you get a bound for your, this is your error bound. There is a big if here, is that we're required to estimate the distance from every pair of iterates. How do you do that? How do you get good estimates for DMN? Well, you repeat the idea of doing optimal transport. So you say, okay, xm is an average of previous iterates, same thing for xn. So let's take PIM is some probability measure, discrete, PJN also. Let's take an optimal transport from here to there. So Zij is a way to send the blue mass into the red mass. And if you do triangle inequality and you plug your previous iterate, then you have an estimate for your next iterate. So you can now optimize over Z. You can take the optimal transport bound, and you have to solve this recursive optimal transport bounds. This is apparently a mess, because you have to solve, for first, the operator plays no role anymore. Everything here depends only on the probabilities and on this recursion. So it's a double recursion in R with 2 indices and an M. In fact, you can do a lot with this. You can compute this. I will not show you example, but maybe later, who is interested, I can show several examples. And what's a bit surprising is that we only use triangle inequality, but the bounds that you obtain by this way, both the DMNs and the Rn, the error bound, they are tight. So I can build an operator which attains with equality every one of those inequalities are in fact as equality. So if you only rely on triangle inequality, you cannot expect to do better than this type of recursive. So here's the result. So here's the iteration again. So let's call tau n the sum of alpha k and 1 minus alpha k up to n. So I'm assuming that this tau n goes to infinity. Let's introduce this function sigma of y. I will use it later. It's basically 1 over square root of pi y. It's a real function. Y is a real variable, and it's just this one. So the error bound tells you that the norm of xn minus t of xn tends to 0 like 1 over square root of tau n with an explicit constant, which is over here. So you have an explicit error bound. After n iterations, you can predict if you want to impose this less than epsilon, you know what to do. In particular, you get convergence just by adding that tau n goes to infinity. Okay, that's for the deterministic case. What about errors? Well, here's what happens with errors. Suppose first that I have a control over the errors. So let's suppose that En is just a computational error under our control. Then you can refine the analysis, you can repeat the analysis, and come up with this type of bound. So here you find again the noiseless bound plus a convolutional term where the error comes in, multiplied by this sigma tau, which is going to 0, plus a residual error at the end. So you can prove this type of bound. And again, under suitable conditions, you can deduce that the full iteration converges to a fixed point. Notice that I never assumed that the fixed point was unique. So it will converge even if there are many fixed points. This iteration will select one of them. So here is just an example. If you take, for instance, errors that you control like a power of your tau n, then you can have these more explicit estimates. We're done? 1 minute, last slide. I jump this. So what happens if you have stochastic errors? You cannot apply directly the previous strategy. Why? Well, simply you would require the error go to 0. That's way too restrictive. So what you do is instead of looking at the original iteration, you do some averaging, and then, let me jump here. You get, again, this error bound, where nu k minus 1 is the variance of the reduced noise. So you have an explicit bound, so I end up with this slide. So you apply now directly this result to the RQI Q-learning, and you get that the expected value of your original iteration, notice that here is the residual with respect of the original map. We introduce the f of q, but here it plays no role. So the real error bound is less or equal than a constant that you can compute divided by square root of tau n. And that's it. Thank you very much.